It's a great pleasure to kick off this evening's event. I'm very pleased to do so. We have a distinguished speaker, Tanay Karnik, speaking to us from Intel Labs. Let me just say a very brief word about the context of this particular lecture. Is a workshop that is being convened on 3D integration for high-performance computing systems. And I would just like to say a word of thanks to the conveners of that conference, Jonathan Chow and Helen Lee of the Department of Electrical and Computer Engineering at NYU Poly, and also Yuan Shi, the Associate Professor in the Department of Computer Science at Penn State University. So my thanks to them for convening a very high-end workshop here at the NYUAD Institute. And my gratitude to them also for inviting this evening's speaker to give this public address in the Intel Labs. Tanay Karnik holds a PhD in computer engineering from the University of Illinois at Urbana-Champaign, which he earned in 1995. And from 1995 to 1999, he worked in the strategic CAD lab at Intel, the computer-aided development. And since March 1999, he has led the power delivery, soft error rate, and low power circuits research also at Intel Labs, where he's principal engineer. His research interests are in the areas of variation tolerance, power delivery, soft errors, and physical design. He has published over 40 technical papers, has issued 46 patents, and has 32 patents pending in these areas, which is quite an astonishing achievement. He received an Intel Achievement Award for the pioneering work he has done on integrated power systems delivery. It's a great honor and a privilege to have Dr. Karnik speaking to us this evening. Please join me and welcome him to the podium.
So when we say staying ahead of the technology, it also means process technology. We have a process that is at least a generation and a half ahead of our competitors, and in the Intel Labs we have to be ahead of our own technology. We have to have applications and systems that are running on a technology that is already ahead of the rest of the market. So what do we do for that? We invest in innovation. We have been investing in capital investments, in plants and equipment. Even in a downturn, Intel never stops investing. We continue to build our fabs. Our fabs cost about, these days, $3 billion per fabrication unit, but we continue to invest. So these two charts are just showing how much we are spending in capital investments and how much property that we are investing in billions of US dollars. So it goes up and down. There are high levels of investment, about 7.3 billion. So right now we are around 5 billion, but we are still investing. Part of the reason is capital investment has been, it does not depreciate. Fabs continue to run. We try to make use of the same technology and take the same fab and operate it on the next node. So things continue. On the research and development side, we have a 10-year total of hitting $50 billion today, and that has been growing, in fact. And we started at 4 billion 10 years ago. Now we are at 5.7 billion per year. So we are investing heavily. We are an industry, we are not a government organization, but we are still investing heavily into research and development. So the mission for Intel Labs. Intel Labs is an entity that is directly reporting into the main organization of Intel, that is CEO. So our CTO, who is head of Intel Labs, directly reports to our CEO. Labs' mission is to do world-class research. Obviously, we have to be in the research forefront of the research in various markets, various aspects. So we are driving Intel's technology pipeline and creating new Intel opportunities. We have to create new businesses, new products, new systems, new applications, new softwares for Intel products. We are a silicon manufacturing company, and we have to feed the silicon manufacturing capacity that is coming on board. Every single year it's improving. We are known for our efficient technology transfer. So we do invent something or innovate or build something in Intel Labs, but it has to show up into Intel product. How does it happen? There are pathfinding teams. So product teams have their own teams. Intel Labs has its own teams. The two teams come together to make something serious and happen and then we make the business unit successful. Business units, in rough sense, we have market differentiation of server products, client products, which are desktops, we have handheld products, and we have smartphone products. And then we have very strong research partnerships. We engage with leading thinkers, we partner with external academia as well as industry. We do not stop at only academia. We have various partnerships going, and we make sure that everybody succeeds in the grand scheme of things. We have some partners from IMEC here who know that Intel is partnering with IMEC today to build new technologies. As I said earlier, our CTO is reporting to our CEO, Chief Executive Officer, and then under the CTO umbrella of Intel Labs, there are various functional units and there are some support units. So in general, in the research organization, we have organized the research into circuits and systems research. I'll go through what all of these mean in the next few slides. Then there is microprocessors and programming research. There's integrated platforms research, which is primarily our SoC related research. Then extraction and experience research, interaction and experience research, which is our new uses of computing and ethnography kind of division. Then we have a separate entity called Intel Labs China. There are some folks who are involved in China here. They know that Intel is heavily investing in China, and there are big units and large number of employees in China. We have a strategy and planning division. Then academic programs and research that is working towards academic research and government consortiums. And then Intel Labs Europe, that is another entity which is primarily working with the European Union to make Intel successful in the European market. So in general, when you look at the broad agenda of Intel Labs, although we are a silicon manufacturing company, the labs look at different aspects of the design and product cycle. So we are looking into people-centered design. So how can technology how can people make use of technology? Immersive experiences, high throughput computing, visual computing, that comes under that. Human-machine interaction. Then communication is a big aspect of the whole puzzle. It's not just the computing, it's also communication. Then in personal energy management, we are looking into new energy systems, new smart grids kind of control algorithms to save energy, optimize the energy usage. Electric vehicles are coming into market, so we do have a unit that is looking into what happens if every single person buys an electric vehicle and plugs it into electric grid in the evening. There is going to be a large load on the system. Somebody has to take care of it. Then security and trust. Security is one of the corporate level agenda. We have to make our systems secure. Cloud computing is already happening. We are actually designing an Intel Science and Technology Center around cloud computing. Then throughput visual computing, many core architecture comes from our silicon manufacturing capacity. And then we are also looking into silicon photonics and electronics. How does photonics get into our systems? If we look at how many academic partners we have many partners. I'm not listing all of them. Recently, UAE University also became a partner. So roughly, it's not just US centric, it's everywhere, all over the world. We are covering almost the entire globe and trying to build talent into the entire globe so that people will buy Intel products and Intel will also benefit from what is the talent that is available. Individual labs inside Intel Labs, so there are individual units in the Intel Labs and they have their own agenda. They are striving to make Intel successful in various aspects of technology development. One of those is circuits and systems research. I used to be part of this for a long time. So there we looked at silicon electronics, silicon photonics, bio devices. We do look into biosensors and biosensing. Then scalable operating systems, virtualization, we look into that this particular systems research lab. And then security and trust. We will have an Intel Science and Technology Center on security also eventually happening. And then we have an independent project funded by DARPA on exascale computing. And there are multiple teams across geos inside Intel who are working on this exascale computing with university partners to make an exascale desktop kind of power envelope. Then we look at the organization is microprocessor and programming research, where obviously because it's microprocessor, we look into microarchitecture research. Emulation, meaning if new instruction sets are coming in, new modifications to Intel products are happening, then we try to emulate before actually making it in the manufactured silicon. Many core architecture, many cores are happening. We had 80 core processors, then 48 cores IA processors. In the market today, we sell 10 core processors. Then advanced on-die fabrics, how do we interconnect all of this? How do we do heterogeneous computing? Then there is graphics and immersive computing to show that we have a product line on the graphics side, so the graphics work feeds into that product line. And then high throughput computing, which is essentially for financial applications. You need very high throughput and quick server applications, so we look into those computing in the microprocessor and programming research. Then another organization is integrated platform research. This is mainly for SoC. SoCs mean silicon on chip, system on a chip, and they are looking into the handheld devices, embedded computing, smartphones, netbooks, everything that is below notebook kind of power envelope. So anything that is around 1 watt to 5 watt or sometimes even sub 1 watt. So in that sense, they are looking into SoC fabrics and accelerators, then digital radio circuits for wireless communications, wireless architectures, new protocols to do the wireless communication from one unit to another, machine to machine communication. Then platform level physical design and platform level packaging, what can we do to make things smaller and smaller, for example, 3D integration. And then converged platform, so you have to do modeling, you have to build tools, you have to make a time to market really short compared to any of the rest of Intel's product cycle. This particular product cycle is very short, so we have to churn out new products every 6 months. Then comes the non-engineering side of Intel Labs, which is the interaction and experience research. Here, I just recently had some conversation with NYU folks that you have departments on liberal arts or arts and humanities. So this is one particular area where we also invest in. We are not just a technology company. We look into social research, ethnography, what happens to life with digital technology penetrating into common life or rural areas. Human-machine interactions, how do the humans interact with machines? Are there any other ways than just typing and speaking in English? Context and inference. Next generation devices, there are some new devices that are coming in, how do we use them? And then people-centered experience. It has to be useful ultimately to a common user. Everybody should be able to afford and operate a computer. Because I'm in Abu Dhabi, I'm outside US, so I'm also presenting two different aspects of Intel Labs. One is China, where we look into embedded computing and applications, cloud interactions. So China Intel Labs is big, it's an organization by itself, and it also looks into machine-to-machine wireless communication, video mining, metadata generation. They are very good in software development, so they are more focused on the software and the application side. And the other side of organization outside Intel, outside US, is Intel Labs Europe. That has about 22 labs across Europe, and that spans across 10 countries. We are partnering with FP framework program FP7. There is an organization in Ireland that belongs to Intel but works with FP7 partners. Then they look into enterprise systems, services, sustainability. There are labs that are looking into many core architectures. There are some units that are also part of other labs. And the European lab, Intel Labs Europe, is also looking into embedded and automotive applications. We had some long-standing relationship with auto manufacturers in the Europe, and we are continuing to have that relationship going forward. With that, I mean, that was a broad overview of Intel Labs. Now, why do we do all of these things? What is happening that requires this much computing and that requires this much integration density? Some of the things that are happening are the application side. So we had, in the past, we had something like textual multipurpose applications where you did not have much graphics on your computer. Then we moved into visual computing and mobile computing, and entertainment came into a picture as your computer started becoming an entertainment unit. When that happens, instead of a single core processing, you need multiple cores to do these processings and simultaneous parallel applications. Then you go into a realistic applications where you feel like you are immersed into a computing applications, you are doing social media, you are doing perceptive computation. Then from multi-core, you automatically move into many cores. You now need many cores to do the same applications. So the user experiences are evolving, and in order to cope up with the experiences that user requires, we have to put in more and more cores. That means we need more integration capacity, and we have to come up with more denser solutions. So this presentation, I am not showing the technology scaling chart, but Intel is continuing to go towards 22 nanometer, and it will go further. So Moore's law is scaling, the scaling is continuing, and we are getting more integration density. Other thing that requires performance scaling are energy efficiency. We have to be energy efficient. We have to use less and less energy for the same computation. Designs are becoming complex, so we have to grow on the architecture and design side to make sure that the complexity is handled. New programming models are coming into picture, we have to support them, and then applications as we showed on the previous chart. So all of these new happenings in the computing world are demanding better and better computers. We had cloud computers even earlier. There were cloud data centers that existed. There were thousands of network computers that are partnering with each other. Google has various computers that are at various locations, so that there is redundancy and there is fault tolerance. There are millions of threads and petabytes of data that are communicating among these computers. There is an opportunity, by the way, here. So we can actually make it lower power, higher density with integration capacity that we have. And the way to do this is, instead of having blade servers, we actually in the lab showed that we can have a data center on a single chip itself. Why have a big data center when you can have the same capacity inside one single part? And that is the one that we call as single chip cloud computer. And that is going to be our next many core computing platform, where the entire data center fits onto an envelope like a laptop. And so we went through an exercise of making data center on a chip. This chip was presented at ISSCC of 2010, and it was called single chip cloud computer. It has 48 IA compatible cores on the same die. It was built in 45 nanometer technology of Intel, high K metal gate, and each 2 cores had a network, and the 2 cores mimicked a cloud node at the chip level, and then they were communicating with each other. The power management was so efficient that we could change the power consumption of this chip from 25 to 125 watts, completely programmable. And it supports very highly parallel, something that can scale out programming models. So if you have a parallel applications, you have a server application that can easily map onto this. This program already exists in academia, that these machines are given to various programmers in academia and industry, even in Microsoft, to make sure that many core programming is actually getting built, so that Intel will come up with products tomorrow, and the software is already there to run on those new machines. This is just a snapshot of the chip to show what we had on this chip. It was a very large chip, 26 millimeter by 21 millimeter. Not going through the details of the die, but it just shows the 48 cores, and so there are 24 regions, and each region has 2 cores. This is something internal to the die, internal to the core. Each cores were interconnected with router. Each unit of 2 cores had their own caches, and then they had a router inside. And it was the total intra die bandwidth were 256 gigabytes per second. That was the bisection bandwidth at which they were communicating, or they can communicate. For the power management, because these are 48 cores, that means you have 48 times the power if everything is running simultaneously. That means you need a really fine control on how the chip is operating. So hence we had voltage and frequency islands. There were 7 different voltages, 6 for the different cores and 1 for the router, and then other memory controllers and IO controllers were running on their own voltages, and then each core could run on its own frequency. So you could, if you have access to this particular machine, you can do voltage and frequency management, and you do the optimal assignment so that you get an application running at the minimum energy possible for a particular frequency. Just a picture of the test board. That test board is big. I mean, it's not very small. It needs a big heat sink so that we can cool this much power. But we got this chip. This chip runs. We can boot 48 different Linux operating systems on 48 different cores, and we can do inter-processor communication to show that we can develop parallel programs on these machines. This chart is just showing that when we measure and optimize the measurement for all 48 cores running, what happens to the performance or frequency as a function of voltage. So in terms of core, the core runs at lower frequency, but the router runs at higher frequency, and at the highest voltage point we could hit the router almost up to 2.6 gigahertz, while the core was up to 1.3, exactly half of what the router is running at. And the voltage could span from about 550 millivolts to 1.3 volts. So there's a large programming capacity in this chip. This chart is showing the measured full chip power, and if we look at the active power and leakage power, percentage leakage power was not really high for this active leakage power for this particular chip. Even at 201 watt time power point, which is at the 1.28 volts, leakage power was less than 20% of the whole puzzle. The typical voltage point was 1.14 volts, and at which we had 1 gigahertz cores. So that means all cores were running at 1 gig at 125 watts, and the mesh was running twice, 2 gigahertz. When this product or Intel Labs prototype, we should call it 48 core prototype, that was given to different academic institutions and industry, we got lots of nice quotes back. So there were 2 quotes that we are listing here. I am not going to actually read them, but this single chip cloud computer platform was very famous. We got good responses from ETH Zurich, and we got a good response from UPCRC, which is Universal Parallel Computing Research Center at Illinois, and they loved this system. They are programming this system and getting maximum out of these systems of 48 IO cores running on a single chip. So I'm now going to switch gears. So that was about many core programming, but what is happening is number of cores are increasing on one side, on the server side, and on the handheld side we are pushing the power down, and we are not really increasing the cores. Sometimes there are only single cores on our parts. So what's happening? Intel has to create different solutions for different markets. Power varies from really high to very low. Workloads are varying. Cooling solutions are varying. Power delivery solutions are varying. And all of these are causing a problem with product development. We cannot have practically individual teams for individual products. So what are we trying to do? We are actually trying to do is we want to make very few designs, but we should serve all the market segments. How do we do that? We have something like a common core strategy, where we try to reuse the same core in multiple products, and we have common process strategy, where we try to use the same manufacturing process across different products. Then we have a tick-tock model, where we change the architecture once and we change the process once. So process only changes every 2 generations, and architecture also changes every 2 generations. All of these things are kind of practical considerations to make so many diverse products happen in a single company. So in terms of doing this voltage frequency trade-offs and when we do for energy efficiency, this is a picture that is just showing what a platform looks like, realistic platform that will look like. You have some cores with caches. Cores will have their own common cache, and then there will be a second level cache and a third level cache. There will be memory controllers, scalable on-die fabrics, some accelerators on the die. All of these units on a single die need to be controlled. And they need, so this control is not an easy puzzle. It needs voltage frequency regions control, it needs power control, scenario based power allocation. You need to allocate energy according to where the need is. There has to be dynamic control, there has to be workloads that need to be mapped on all of this. But this single unit of platform, this single platform has to do multiple things so that we can give the best user experience possible. So in the labs, we started looking into what can we do. One of those things is dynamic adaptation and reconfiguration. So we have sensors on the die. We actually work on different kinds of sensors that are integrated into the die, that are sensing various things that are happening. And according to those sensed voltages or sensed currents or sensed temperatures, we actually change the voltage and frequency or the operating point. So it's a continuous loop that is automatically adjusting itself so that you get the best energy or least energy possible for a given computation. One example is resiliency. So we build resilient platforms that are doing the error detection. So they are kind of letting errors happen, but they are correcting it before the error actually becomes visible to the user, the eventual user. So the resilient platforms are looking into all the way from applications to circuit design, programming systems, operating system, virtual machines, firmware, microcode, microarchitecture, circuits, everything is resilient. And we are trying to let some errors happen where we are correcting them, and during this process we are trying to gain energy. We are trying to get the same performance, error-free operation back for a lower energy point. And resiliency is a big objective in Intel labs, to make across the Intel labs platforms completely resilient and robust in operation. We also are working on fine grain power management. So how does the fine grain power management happen? You need voltage regulators. In the old sense, you had one voltage regulator that was supplying the same voltage to multiple cores. Now you have multiple voltage regulators that are individually supplying different voltages to different cores. Those voltage regulators are still off die, but what is the lab trying to do? We are trying to optimize the voltages, we are trying to optimize the interfaces. And how do we do that? We actually bring those voltage regulators on the package or sometimes on the die. We are trying to show that we can do these voltage controlling units, we can actually put them closer to the microprocessor. And this is one of the examples where we had a voltage regulator chip and we had a microprocessor chip on the same package. And this chart is showing how we can actually control. We can convert high voltage to low voltage, hence we bring very low energy in. We have less losses to bring the low current in. We distribute these voltages and currents to different platforms, and then we have a very fast control to make sure all of this puzzle is fine grained and it's energy efficient. We also do something called as load adaptive power source. So the power supply, I mean in an electric wall you have a constant power supply and you are drawing current. Here we are drawing whatever current is required, we only draw that much, and we switch off the power supply, part of the power supply that is not required. So all of this can happen because you are fast and you are closer and you are in the silicon technology that is actually requiring this kind of operation. Other thing that we look at are the accelerators. We know that Intel does general purpose computing, we make microprocessors which are on the left side, but they are not very energy efficient. In order to do the same function energy efficiently, you need dedicated hardware that is programmed to do a particular application. We try to meet somewhere in the middle by digital signal processing that gives you 10x energy efficiency. So we trade off efficiency for flexibility and get the 10 to 100x higher performance, and we try to optimize the gigaops per watt. In order to do that, in Intel labs we took some examples, like for one example is multi-voltage cache. In this scenario, in a typical processor, cache is on a separate voltage and it's staying at that voltage, its voltage doesn't change. In reality, all caches on all microprocessors that we sell do not have to operate at the same voltage. There is some software rate limit on the voltage. You can even go lower for worst case voltage, minimum voltage, and the nominal array minimum voltage operating point is even lower. Why can't we go lower in the cache operating point? And that is what this slide is showing. we come up with new techniques of memory. So instead of 6 transistor SRAM, we come up with 8 transistor cells so that it will go in voltage, go lower in voltage. We also put adaptively, we put the cache on standby. So if you are not reading some part of memory, why don't you put it on the standby voltage or a lower voltage? So that also happens. So some part of the memory actually goes lower on the voltage, and whenever you are reading something, then only it comes to a higher voltage for a fast read write operation. So we embed voltage shift, in the Intel labs we came up with embedded level shifters without sacrificing the memory density. We can embed level shifters, we can embed word line drivers, we can do these voltage manipulations. At the architecture level, we actually program what is the part of the memory that is working at what voltage. So we actually mark in some bit sense that this part of the memory is not working at lower voltages, and do not use this part of the memory at your low voltages. Now the thing that helps us is when you are operating at lower voltages, you also need less memory for operation. So we can switch off partial amount of memory and only switch on the memory that's required. One way of doing this is we reduce the cache size at low voltage and frequency time point, and the failing ways or banks in the memory or lines or sets or words per bits, they are actually switched off. What do we gain? Different ECC techniques are actually giving you at a very high penalty lower and lower supply voltage of operation. But if we do this word disable or line disable or bank disable, this chart is actually showing instead of going through expensive techniques like ECC, we can compared to a conventional, we can get 50% of the energy back for only 5% of the performance loss. So if we are ready to give up only 5% performance, which is also not required at lower energy points, we can get 50% energy back. So these are kind of cache reconfiguration techniques at the architecture level. Then in terms of accelerators that we were talking about, labs did an implementation of a low voltage motion estimation engine, went up to 240 millivolts, which is a very low voltage. And this chart actually showing that if we span voltage from 1.4 volts down to 0.2 volts, then energy efficiency, which means amount of performance that you are getting for the same amount of watt that you are spending, at 320 millivolts we actually had a peak. We had a peak energy. This part 320 millivolt point is actually above the threshold voltage. Some of you may be familiar with the threshold voltage concept. So it's a super threshold point of operation beyond which you start losing energy, because now you are paying more energy in the leakage power and less energy in the active power. With the same voltage manipulation, your amount of power that you are consuming goes on increasing. This is in milliwatts on the right side. Power is increasing and your frequency is increasing, but you are getting, as you go low in the voltage, you are getting a very better and better energy efficient as you start lowering the voltage. Another way of doing a dynamic adaptation is sensing, and we had a chip where we had thermal and droop sensors on the die, and it was also sensing the activity on the die and then adjusting the voltages, clock frequency, and getting the best energy efficiency possible. And here we are showing that with a transient event like voltage droop, you can get about 32% frequency increase by these techniques if the droops do not happen frequently. If these voltage droops are happening very frequently, then still you can get about 23% in frequency improvement for the same power. So you are not spending power, you are not guard banding anything, and you are actually adapting to what is happening on the die. It's like you are sensing and reacting, you are sensing and reacting, but you are giving the perfect operation and error-free operation to the, so user does not see any change. This is an adaptive dynamic operation that happens with voltage and frequency manipulation. When we were confident about doing this adaptive operation, we also went further and we started doing it at pipeline level. So we put embedded error detection and correction in, so embedded error detection at the pipeline level circuits and error correction at the architectural level. And then we taped out a resilient and adaptive core last year or year before last, and then presented it last year, which was again in 45 nanometer, where we could let the errors happen, but catch them before they get committed and then correct them and put them back into the pipeline. And as long as these number of errors are less, they are not more than like 1 in 1,000 cycles, we actually gain energy. The way it's shown is in this chart. So this is the total energy versus throughput. Throughput goes on increasing, but energy also starts increasing. But if you look at the iso throughput point, where you have the same throughput happening, but if you have resilient techniques, then you get 41% better throughput for the same energy point, or you get 22% less energy for the same performance. You can play it either way. You can either increase the performance for the same energy, or you can reduce the energy for the same performance. And on the right side, we are just showing different applications running, and with different resilient techniques, you can actually get throughput gain up to 20% for the same energy. So there's a large gain available by not doing every single thing absolutely correct. You can have some things that go wrong. Sometimes they don't matter. If they matter, you correct them in the adaptive operation. Then this is the previous things were all about computing. We were going into computing puzzle, getting better and better computing solutions. But there is another part, which is communication. Your processor, it may be really great, it may be doing teraflops of performance or petaflops of performance. It has to communicate outside. It has to have an access to memory. What's happening on the memory side? If we look at the client bandwidth requirements, they are about 50 gigabytes per second. Server bandwidths are 100 gigabytes per second, and high-end server bandwidths are 200 gigabytes per second. Very complicated server chips, high-end servers are even complicated. The platforms are looking very dense. They are consuming a lot of power. They are also producing a lot of heat, and we have to solve all of these problems so that these units actually operate efficiently. And this is just the current picture. If you project the future to terascale computing, then you need terabytes of bandwidth to the memory. In the real sense, if you look at 2x improvement in the memory bandwidth every 3 years, that is kind of reality. You draw a line. Let's say in the optimistic sense, you have 3x bandwidth improvement every 2 years instead of 2x every 3 years. These are different bandwidth options. All the puzzles that are happening today are lying somewhere between these two lines, and our requirement is even higher. We have to have even higher bandwidth to get to the memory, because the computing is going faster and faster and communication is not catching up. In order to hit the high-end microprocessor demand, we need terabytes per second bandwidth by 2020, and all of these bandwidth, CPU to CPU, processor to processor, to peripherals, to I/O, to memory, all of those have to increase in the amount of memory that you are accessing. So when you increase the bandwidth, the other side of the story is energy. Now you are going to spend more and more energy into this bandwidth. How do you bring this energy down? Today we have about 20 picojoules per bit kind of energy expenditure, and hence your I/O power is up to 32 watts on a single machine. 32 watts is a large amount of power that you are spending for just accessing the data, not actually doing anything with the data, just bringing the data. If you need 1 terabytes, now you need 160 watts, which means you are going to communicate with more power than do computation. Your computation will be cheaper in power, but in order to bring that data to the processor, you are going to spend more energy, which is not a good solution, because these communication power numbers, they don't stop. I mean, communication has to be alive. It cannot go into the standby state. That means you are going to spend this much power even if you are not doing anything. So what do? We try to bring the power efficiency down. So we try to consume less picojoules per bit every single year. We are trying to reduce the channel losses. We are trying to reduce the I/O power. But traditional interconnects are not scaling. Traditionally, when you communicate from a processor to another processor, you are going through a package to a socket to a motherboard to another package to another socket to a package to another CPU. And that traditional interconnect that is going through these kind of laptop platforms where you see a green board where things are communicating, it's not going down. We have to look at some other ways of communicating from one machine to another. What do? In the electrical sense, we have two options that we are investigating. One is flex interconnect. So it's a flat cable, green cable, that instead of going through the board, it actually connects one board to one package to another directly on the package itself, where there is a prototype running, and we can actually show this thing running and working at a higher speed, lower energy. Otherwise, we have a twin ax cable, which is a thin cable, looks like a wire, very small wire, that also can connect from one package to another, and it can go very long. So you can keep one computer here. Oh, excuse me. You can keep a computer here, and you can have the communicating agent somewhere 3 meters away or 5 meters away. So just a minute. So in the different communication or electrical channels that you communicate with, there is one called high density interconnect, which is still a high density board that gives you some power efficiency, but very low channel lengths. You cannot go beyond few centimeters. Then you go to the flex cable that brings you to about 50 centimeters, and then if you have twin ax, you can go up to 300 centimeters, which is 3 meters. So you can go really far with twin ax cables. This chart is showing the losses that happen with different cables, different electrical options. So with a stubbed interconnect on the board to board interconnect, you have really high losses even at 5 gigahertz and below. Hence you do drilled interconnect with backplane, and then you get less losses, so you go up to somewhere close to 10 gigahertz, but not quite. You are still at about 8 gigahertz. Then you go to these flex cables and twin ax cables, they actually bring you beyond 10 gigahertz. So now you are communicating at a higher bandwidth. So 0.5 meter flex and 3 meter twin ax, they can get you to 20 gigabits per second data rate per pin, per connection. So which is a very high bandwidth compared to what we have today. And then why don't we go even further? If today we have a shorter solution, why don't we take a twin ax and make it short, and then you can even go to 40 gigahertz, which means 80 gigabits per second on the same connection from one die to another. So these are like very high bandwidth numbers, and we can take some large amount of memory, bring it to the processor, do the processing, and again put it back in the memory in record transaction time or communication time. So in IO research on the electrical side is focused on increasing the bandwidth and increasing the cable bandwidth for very low energy. On a completely different sense from electrical, we are also looking into optical. We are looking into hybrid lasers, we are looking into silicon photonics. How do we do optical communication instead of electrical communication? And Intel Labs has a big entity that is looking into lasers, modulators, detectors, optical integration, optical packaging, and all of this together inside a microprocessor system, so that we can tomorrow show a bus that is running optically instead of electrically, or maybe the user will not even know that there is optics inside your box that you are purchasing. So this chart is showing the various research vectors that are happening in Intel Silicon Photonics. They have working prototype today that runs at 10 gigabits per second. Sometimes you can push it to 12.5, and if you do 4 times 10, then you have 40 gigabits per second length. There is a completely silicon transmitter, fully silicon receiver, and they are communicating on the optical channel, and very high bandwidth optical communication. They go even further, and then they take hybrid silicon, they put them to multiple channels and then go parallel, because optics does not have any problem with going different wavelengths on the same fiber. So they put more and more data through, and this is a very promising approach to actually get large amount of data flowing inside a system optically instead of electrically. Other side of Intel Labs, I am kind of going faster because we are slowly running out of time. Other side of Intel Labs is looking into virtualization. So what is virtualization? You do hardware software co-design. So you have some host processor, and it has its own operating system. Let's say in our sense it is x86. But let's say there is an application that is written for something completely different. It's not an Intel machine. It is written for something else. Then what do we do is we take the guest operating system and its instruction set, we have our own host operating system, and we put a virtualizing software layer in the middle, so that operating system feeds into virtualized layer and then goes into hardware. So you have virtual machine and you have the actual machine, physical machine. They are operating coherently. You have an operating system visible memory in the physical area, and you have a concealed memory in the virtual area. All of them feed into instruction cache and data cache on the die, and the core actually does the application with virtual support. This kind of virtual hardware software co-design was done by another company in the past, but they did not succeed. But in Intel Labs, we are still trying to see if this makes any sense. A whole bunch of advantages of doing this. You can have the same hardware for different applications. You can actually make hardware simple for complex applications. So there is a dynamic reductions in number of switching transistors, hence power. There is a dynamic adaptation of hardware to software. So take the hardware units, push them into software. That means you can program them, that means they become adaptable. Performance can be also adaptable. The whole solution is scalable, is resilient. So if there is something wrong happening, you can change it without actually changing the manufacturing cycle, which is very good. Backward compatibility, so we have legacy compatibility. We are still supporting old buses, old I/O standards, old arithmetic standards. All of those can still continue. And we also have forward compatibility. So if something new comes up and hardware is not ready, we can do it in software and put it in hardware. So a co-design processor is another aspect in the Intel Labs that's happening. Another system that we have already given to academia to program is heterogeneous computing. This is a new class of applications that are happening, where instead of having the same instruction set and the same processor and multiple of them, why not have heterogeneity? So in this particular system that we already have available, you have a Xeon class machine, which is a server class machine, does a lot of operations at a high power envelope, and you have an Atom class machine, which is doing smaller scale of applications but at a very low power envelope. Both of them are running an application, goes through an OS, and then the operating system decides whether it goes on Xeon or whether it runs on Atom. So operating system decides whether it should run faster or it should run at low energy point, low power or high performance. Once you have an application, the heterocore operating system, this development platform actually decides automatically, runs the applications. It can do server workloads on the Xeon processor, Atom class loads on the dual core Atom, and all of this is happening in coherence. And this is the first real heterocore platform that is available from Intel today to do heterogeneous computing. What is the future? In future, we are actually going into serious heterogeneous computing. So then in this solution, instead of having a single operating system that is feeding the application into different domains, we can do we can have two different operating systems taking decisions differently. So application can fork into different operating systems, and then they run independently and then do the same application more efficiently. Because we had a 3D workshop today, I wanted to add a few slides on 3D integration. So what is 3D IC doing in all of this sense? So we already said that bandwidth is a problem. So in terascale computing, we are looking for teraflops of computing, terabytes of memory, terabits per second of communication. We have to scale amount of dollars per transistor that are costing us to manufacture. We have to scale energy per operation, and we have to scale SRAM bit area every technology generation. In order to increase the bandwidth, we can do the architectural techniques, or we can go wider in pins, which is expensive. Architectures are 3D or multi-chip module, or we can increase the bandwidth, but that comes at a power cost. So in order to increase the bandwidth without giving up, without costing it too much, we are actually proposing the 3D way of doing communication, or processor to memory communication. There are various 3D applications that are being tried in Intel. This one chart is showing that the relative die cost as a function of different technologies, as a function of die size for different technologies. So at a large die size, you have 3x differential between 3 technologies, one technology, versus a small die size, you have only 2x differential. What this means is that you want to have, if you have multiple technologies to be integrated into a single system that you are selling, then you should be on a smaller size, smaller die size. Other way of looking at is relative cost of a die. Relative cost of a large die is 3 times, 15 millimeter on the side die costs you 3 times more than a 10 millimeter die. So that means you want to do smaller dies, many smaller dies. How is 3D going to help? It's going to give you better, possibly better frequency, better RC delay of communication, lower cost, hopefully lower cost, because the delta of 3D integration should be less than that 1x of in this puzzle. It will give you integration of heterogeneous technologies, it will give you interconnect power reduction, and it will provide wide IO standard, wide communication. Another advantage of 3D is voltage regulator integration. We talked about regulator integration on the package in previous slide. Instead of having package level regulator on the side of the regulator, on the side of the microprocessor, we can actually have a 3D integration of microprocessor and voltage regulator in the middle. And all of these red capacitors that you see all over across the system, all of them go away, and we actually communicate at a very faster rate from voltage regulator to the microprocessor. There are some works that are already published in 3D power delivery. I'm not going to go through the details of these, but references are provided. Then looking at processor memory integration, some of you folks have already presented how processor memory integration makes sense. In Intel sense, because we have high power products, we cannot put DRAM in between the CPU and heatsink, so we are proposing the DRAM should be between CPU and package. But even then, the DRAM relative temperature on the DRAM die is increasing up to 3 to 4 degrees centigrade as a function of ambient temperature and the amount of power that is consumed by the CPU at any case. Intel is not a DRAM company, so for our 80 core processor that we presented many years ago, we had a 3D stacked SRAM memory. We do not have access, did not have access to DRAM technology. So we now we did a die match SRAM 3D prototype, and in this particular case we wanted to show 1 teraflop under 62 watt of envelope. These are the two dies. So this is my processor die, this is the memory die. Memory die had TSVs, so there are holes in here. The white holes are the through silicon vias that are connecting through the memory to the processor. There were 80 tiles of processor, 80 tiles of memory, and then this shows the picture of die to die communication. This is the through silicon via. This is showing a cartoon that shows there is an 80 tile processor. This is the thin memory that was thin to like 70 microns in this case. There were 3,200 through silicon vias that went through the memory die that connected this processor's IO power as well as memory to processor communication. The interface between the processor and memory was face to face, which was denser than C4 pitch. So I think this pitch was about 194 microns, this pitch was 97 micron, twice that, so 4 times more capacity. And then other potential 3D applications that we are still pursuing. Again, I'm presenting this as in the 3D sense because of 3D workshop. There is a presentation on network on a chip at the workshop, so I'm just restating that you can do network on a chip on 3D because it solves a lot of network problems and networking issues, fabric issues. You can do clocking, generation and distribution in 3D. You can do sensors on 3D. Again, there are sensor solutions already in 3D in market, but I'm talking about on-die sensors for adaptive operations. You can do signaling, either wireless or IO communication, copper, electrical in 3D fashion. And you can also have an integrated IO hub. In Intel sense, we can have a legacy IO supporting IO hub that does not change, which historically has been called as South Bridge at Intel. So South Bridge can be on 3D and rest of the processor can change. South Bridge can stay constant, which means it will solve the high voltage requirement, it will solve the legacy voltage requirements, all of that requirement. Coming to the end of the talk, because this was various aspects of Intel Labs, what do we do, different projects, I don't really have a summary slide, but we are doing lots and lots of different techniques in Intel Labs. I would like to thank a lot of my colleagues. Everybody helped me into making this presentation happen and bring Intel Labs, what do we do to this audience. I hope you enjoyed the presentation. I would like to go to the question answer session now. And one thing that I would like to do is present this slide in front so that you kind of know what do we do at, what do we do in Intel Labs and different aspects of Intel Labs. Thank you very much for attending and your patience, I guess.
Thank you for the presentation. It was great information. I'm going to ask you about the security and trust aspect.
Sure.
So, are you referring to hardware Trojans, or are you talking about other sorts of security?
No, so we are talking about malware and Trojans, and we are trying to make our systems more secure. So we are trying to come up with techniques so that we can hide a lot of data and make it encrypted, and also the encryption standards. We are trying to put them in hardware and undetectable, so that we can hide the keys, for example, from the user. In terms of malware protection, we are trying to secure some part of data so that it won't be visible. Even if the computer gets stolen, nobody can actually access any data.
So you're referring to logic encryption, obfuscation techniques,
yes,
right? Okay.
But mainly hardware. We are trying to build encryption into hardware.
Okay.
Yeah.
All right. Thank you.
In terms of photonics, is the focus only on the communication part, or you're doing any research in photonics in terms of processing also?
So no, so we are not looking into photonic processing. We think our silicon technology is much better for that. But communication, because photonics has no length limit, once you are in optical channel, then you can go very far.
Exactly, but also in terms of, except for the stability of computation in photonics, processing in photonics, there is a chance of a higher performance in the sense of you will be having much more teracycles per seconds if you're going to move from the silicon.
So it's still a communication problem, what you're describing.
No, but I'm talking about cycles per second in terms of processing too, right? There will be an improvement, I guess, if you move away from the silicon, try to investigate, you know what I mean here.
So you are talking about optical computation itself? Or
Yes, optical communication.
So that is why we are looking into silicon photonics. So hopefully photonics will come from today at some kilometer distances to sub-rack distances to sub-system distances. When that actually starts happening, then we will look into actual, let's say, on-die optical communication. But today we are only off-die. So we go only optics from one die to another. We don't do on the same die optics.
So in your 7-stage pipeline that supports error correction, I couldn't quite understand what you're comparing when you say same energy, better performance, same performance, better energy. What's your base case? What are you comparing against?
I was trying to go there, just a minute. Okay, here. So in this particular example, you had these pipeline stages, like the sequential stages. There was error detection here, and then error detection, and then there was an error control unit here, and then adaptive clock control unit here. So when we compare two things, in one case we have a constant clock feeding in, all of these things are off, none of those is working, and they are sleeping. I mean, they are not consuming much power, they are in the leakage power mode. And then we run this machine, and then we come up with some particular point of operation, frequency of operation or energy of operation. Then we switch on all of these and try to gain performance or lose energy or save energy.
Okay.
And then come up with another point. And because of that reason, they don't exactly align. I mean, that, like, we cannot get one point exactly at the same point as this one, but we try to map them against each other.
Yes, hello. I understand that you have a unique program in working with University of California, Berkeley, with, I guess it's an Intel lab right on the campus. is that similar to what you have at Calston? Could you talk a little bit about what sort of research program you have there as far as it's a university Intel collaboration?
At Berkeley?
Yeah, no, at Calston. Is it?
At KAUST?
Yes,
Okay.
because
So
that's kind of more regional. You
yeah.
know,
So KAUST regional, KAUST is mainly today, the functional part is on photonics, like they are looking into photo detectors, some hybrid photo detectors, and they are looking into bio delivery, so drug delivery. Going forward, KAUST will work with us on new elements and non-Boolean computing. So they will look into some element that they don't have a clear Boolean operation, but we can still get functionality out of it. So KAUST will work with us on that. No. So in the Middle East region, we have something called as MER program, Middle East Region Program, and partners of those is KAUST and KAXT, Cairo University, Nile University, American University of Beirut, Istanbul, University of Istanbul or University of Turkey at Istanbul, I don't know, one of those, and I'm forgetting one. There's one more.
Kuwait University, maybe?
Pardon me?
Kuwait University, maybe?
Kuwait University, maybe, yeah. And obviously, I mean, we work with Technion in Israel, but Israel is, I mean, we have big Intel in Israel. I mean, there's.
It seems like you're trying to get everything onto the die, if at all possible. Are there things that you anticipate you cannot get onto the die, or that you see as, you know, too far in the future at the moment to be considering?
I'm sorry, I didn't understand.
Well, you've moved your voltage regulator onto the die, and you're looking at bringing other things into the die as much as you can.
Right.
Are there things that you anticipate that you can't get there, or that you don't want to at the moment?
So there are things that we cannot, at least today we don't have a good solution about, like for example, magnetics. So magnetics, although we can integrate magnetics, we cannot integrate at the scale of what we are looking at, not very really small miniature magnetics. So in that sense, we still have to stay on the package. So in the solution that we are showing, or results that we are showing, we still have package mounted inductors, and everything else is on the die. So that's one puzzle that we haven't solved. We have to bring that. Then in photonic sense, we do not have a laser on the die yet. We are not generating light in silicon. We tried, we have some papers from Intel on silicon based light generation, but it is extremely low efficient.